With all this technology coming in, computer components are starting to get smaller and approach the size of a single atom. However, this tiny scale is a real problem. For transistors of a size relevant to an atom, electrons will transport to another Bloch passage via quantum tunneling. In the quantum world, physical matter exhibits properties of both particles and waves, the point where classical computers found their limitations, and here quantum computers come into play. These computers are horribly fast and can solve thousands of equations in just 10 seconds, which make them unique and different from the classical ones. Unlike classical computers, which use bits as the smallest units of information that can exist in one of two states, 0 or 1, qubits can exist in multiple states simultaneously, 0 and 1. This verifies a quantum phenomenon known as superposition. For example, when a photon encounters a beam splitter, it can either be transmitted or reflected. This photon is in superposition of being both transmitted and reflected unless it is detected to collapse then in one of the two states. This allows quantum computers to perform various tasks at once. As the number of qubits in superposition increases, the number of possible combinations grows exponentially, where 20 of them can store more than 1 million values in parallel. Another fascinating phenomenon is represented by the concept of quantum entanglement. It is when two or more particles are interconnected in such a way that the state of one particle affects the state of the other, regardless of the distance separating them. For example, two electrons are entangled with each other. By knowing that one electron having a spin up, we can deduce the spin of the other by being the opposite, which will be a downspin. Similarly, a state of one qubit can instantly affect the other, unlike bits that changing one will not affect the other. This correlation demonstrates the non-local nature of quantum mechanics. Interference is another significant concept that enhances the likelihood of correct outcomes by manipulating the probabilities of qubit state by interference. It arises from the wave-like nature of quantum particles. In quantum algorithms, constructive interference is when two or more amplitudes align together in phase and add together, which in turn increases the probability of a certain outcome, amplifying correct solutions. On the other hand, destructive interference is when the amplitudes are in antiphase and subtract each other, which in turn decreases the probability of certain outcomes and cancels out the wrong answers.